So I'm the chair for these talks. So I just wanted to welcome Kamatani from the Tokyo. We'll be talking of course about many guided metropolis kernel.
Thank you for the invitation. So this is joint work with, this is Kengo Kamatani from Institute of Statistical Mathematics. And this is joint work with Shaolin Song, who was in Osaka University when this paper has been published. Now he's in Takeda Pharma. So anyway, this talk is about Markov chain Monte Carlo method. And Markov chain Monte Carlo method became very popular in Bayesian statistics in these 30 years and heavily used. So we know many things about MCMC, but at the same time, we gradually understand the limitation of MCMC, and one of which is reversibility, which I will explain later. And due to reversibility, MCMC does not behave nicely in some cases. And this talk is about extending reversible MCMC to non-reversible ones. So non-reversible MCMC is not new, but there are not so many non-practical MCMCs in the Bayesian statistics. So in this talk, we think about some kind of framework to construct non-reversible MCMCs. So let's get started. So since we are interested in Monte Carlo method, so there's a target distribution. We write this I x dx, and we want to approximate integral with respect to this distribution. And in Bayesian statistics, this is posterior distribution, so it's very complicated. So we want to approximate, and one of the approximation method is MCMC, which is based on the law of large numbers. So I like this form of law of large numbers. So let E is a state space, and the Markov chain is pi invariant, which I will explain in the next slide. Anyway, under this condition, together with a very mild regulative condition, this can be actually even milder, but I like this form anyway. So under this condition, if x1, x2, and so on are from Markov chain, then there's a law of large numbers. And if pi is very complicated, such that and high dimension, or there's so complicated properties, and if you can simulate x1 and x2 easily, then there's a benefit of using this to approximate this integral. And this is a Markov chain Monte Carlo method. So it's nice. So what is pi invariant? So the essential property for the law of large numbers to hold is pi invariant. Now, what is pi invariant? It's a not mathematical definition, but anyway. So Markov chain determines random flow in the state space. And the pi invariance means as follows. For any subset A, the probability leaving state A is the same as that entering A. Under this property, so there's a balance. The probability of A does not change through the iteration. So this is pi invariance. So under this condition, MCMC has a nice property. But this is a rather global condition, which relates to many states in the state space, and which is relatively hard to control. But fortunately, there's a nice sufficient condition, and this is the reversibility. The reversibility means as follows. For any subsets A and B, the probability going A to B is the same as that from B to A. So under this condition, we have pi invariance, but pi reversibility is much easier to control, much easier to manage, because essentially this condition is between two sets, and essentially this is actually the condition between two states, so it's easy to manage. On the other hand, pi invariance, we need to control many states, but this is much easier, just two sets. So thanks to this simplicity, reversibility becomes the basis for almost all MCMCs. So almost all MCMC is reversible, or it's product of these reversible MCMCs. However, this property is not ideal because if one jumps from one state to the another state, there's a probability going back to the original state. So due to this fact, sometimes MCMC can be diffusive. It does not move so much. So reversibility is the basis, but at the same time, this is the bottleneck to the performance of MCMC. So there is an interest for non-reversible methods. And this is illustration of the comparison between reversible one and non-reversible one. And orange is reversible MCMC. Actually, it is from random walk Metropolis, which is most traditional MCMC. And the green one is just a small extension of the traditional one. And this is proposed by Gustafson. So we call this method Gustafson's method in this talk. So green method has much global move compared to orange one. And orange is sometimes looks diffusive. So green is actually better. Looks better, but actually better. And there's also some theoretical consideration about the comparison between non-reversible and reversible ones, such as Diaconis, Holmes, and Neal. They compare the performance of reversible ones and the non-reversible counterparts by several measures. Also, recently, Andrew and Livingstone compared the reversible and non-reversible by using nice ordering properties, so-called Peskin ordering. I skip here. So, however, designing non-reversible MCMC is not an easy task. As I mentioned, reversibility is just 2 points, but non-reversibility, we need to care so much points. And the Gustafson method is nice, but essentially only work for one-dimensional Euclidean space. And we would like to extend this algorithm to more general state space. And this is our talk today. And actually, our talk is related to direction. Actually, the method I explained in the previous slide is, direction is an important property, important matter. So in the green method, this is actually also has a direction variable. So initially, this is heading to negative direction. And it keeps negative direction this way. And MCMC has a two-step procedure. First, propose, and then accept or reject. So if it is accepted, we still keep going to the original direction. And when it is rejected, we switch the sign and going upward to the next rejection, and so on. So the direction is actually, yes? So this is a time index. X is time index, and Y is the state. So if the state, so there's a global move, we think that this is a better, and globally does not move so often like this one. We think that this method doesn't work well. So X is, I have to say that the X is a time index, and the Y-axis is a state. So this is one dimension. This picture is enough. I forgot. I think that this is T distribution is a targeted distribution, if I remember correct. Because there's some points are very far from the origin. So I think this is T distribution. It's just a by chance, I think. There's no weight on zero. I think it's just by chance. So is there any other question or comments? Okay, let's move on. So I'm here. So there's a direction. So in this talk, what we want to do is very simple. We want to extend the original algorithm into more general state space. And what I want to do is as follows. So actually, we can apply Gustafson's method into multidimensional case, but it is not ideal. So we may call that this is positive direction. So it is two-dimensional case. So we think we may call that this is positive direction, and this blue is negative direction. But maybe smaller dimension, it is okay. But when dimension becomes higher and higher, probably this direction is tangential to the target distribution. So it doesn't make sense for high dimensional case, I think. And I think what I want to do is a more informative direction, like this one. So if I go to the center, we can say that this is negative direction. And if we go out from the center, we may call that this is a positive direction. So this is all, both of which is two-dimensional case. But I think that this is more informative. So what I want to do is this one, not this one. This is possible, but this is, I think we have to develop something. So this is our plan. It's not so complicated, very simple idea. So the idea behind Gustafson's method, the green method, is as follows. For any state X, we divide the state space into two parts. The bigger parts or smaller parts. And if positive direction is selected, we will go bigger and bigger. And if negative direction is selected, we will go smaller and smaller. So this is the idea. So any state X, we divide that into big and small. And we can do the same for multi-dimensional case. But it's not easy. We also have to assume this condition. Without this condition, we have to change original MCMC drastically. And we don't want to do that. So we want to make the original MC structure very simple. And I would like to just
Sorry, you tell us what is going on? Yeah, but if you're going to touch, just tell us, because otherwise he's speaking and you're interrupting. Okay, it's over now.
Thank you. So our step is as follows. It's an easy step. So first, you don't consider about the general state space, but consider only a very small space. It's an order statistics because these are designed dependent on order. So for example, if you consider D-dimensional Euclidean, D-dimensional Euclidean space, we first observe order statistics such as squared norm, for example. And first we design unbiased kernel on this space. So this space is on the positive real line. So we consider order kernel on this space. And then replicate this construction in the original state space. And then make sure that everything is fine. So this is what we want to do. Okay, so let's move on. So first we design a simple kernel on smaller space. And it's nice to compare the original method and what we want to do. So what we want to consider the simple state is as follows. We want to introduce order. So the set have to have this kind of order relation. And also we assume that the order set is actually group structure, and group structure does not break this order relation. So the small set G has an order structure together with group structure. And also in the original space, Gustafson's case, they consider one-dimensional Euclidean space. And in that case, Lebesgue measure was underlying measure. But in our case, we consider unimodular Haar measure. It's not complicated yet. This is nice properties. Haar measure has scale invariant in this sense. So product with respect to G from left-hand side and the right-hand side does not change the measure. And also the measure on the set S is the same as that of the inverse. Of course, Lebesgue measure satisfies this condition. So we want to generalize it to more nice space. So that's the comparison. The left-hand side is Gustafson's original kernel, and the right-hand side is a general case. So in the original kernel, order set is one-dimensional Euclidean space. And the general case, G, which is locally compact, topological, and ordered group, it's totally ordered group. And the Lebesgue measure was the underlying measure. And the general case, we consider unimodular Haar measure as the underlying measure. And the important measure in the Gustafson space is symmetric measure, because actually Gustafson method uses random walk metropolis. So they use random walk. So they use this kind of symmetric measure. And the same one in general space is this one. And we consider random walk kernel on the Gustafson case, which correspond to this one on the general space. And if we consider like this, we automatically have unbiasedness. So this is what we want to do, at least in the small space. So now everything is fine in this small space, G.
Sorry. Yeah. Can I maybe interrupt the question? Yeah. Oh, I have to auto close. Okay. I kind of, you flashed the slide on when you were talking about the SR sets from, okay. And so when you say S inverse, is that inverse with respect to which operator? Because it seems like minus S on the left is with respect to the addition. while S inverse, if it's like a matrix, maybe it's with respect to multiplication. If I think of RD, for example.
So RD case is RD is a general space, and the first we consider small scenario, and in this case we consider, for example, R plus,
right,
positive real number. So there's a group structure, so we can easily define inverse of our set. Yes, group structure.
Okay, so in general, for a general group, but it will reduce to the Gustafson construction if I use the R plus.
Mm-hmm. Yes.
On the right there, you have the general case, but you still wrote the same as before on the left, the last line.
Yes.
Shouldn't it be changed?
Yes, that's the point. Sorry, I have to explain. So in the left-hand side, it's easy to understand for this structure, but the right-hand side, I have to explain what this is. So this state it means that the all elements which is bigger than X in this order topology, and the same one. So this is all elements which is smaller than X in this topology. Since this state space is totally ordered, so any sets can be compared. So this is what means is just a set based on the order. Okay, so everything's clear if you have this structure, but one thing we have to do. So if we have this symmetric measure, we are fine. But of course, in the beginning, there's nothing. So we have to consider how to make the symmetric measure. So now we are going to the construction of this kind of measures. So how to design gamma? And this is the answer. Because if nu is a unimodular Haar measure, which we assume the existence, then if the measure gamma has density small gamma, which has these symmetric properties, then we have symmetric properties. So it's easy. What we want to do is find nice function with these properties. But we want to go one step further. So how to design these functions? And there are several ways to do this. But in this talk, we consider the following construction. So how to design this symmetric function. And we want to do by using, say, reversible function. Reversible because A and B can be exchangeable. So by using this reversible function, actually this is related to reversible kernel. Anyway, using this reversible function, then gamma can be defined by mixture of H and nu. And if we define like this, gamma has symmetricity. So it's easy but long, so I skip what's going on. But anyway, gamma is symmetric. So the now target is this function. If you have this function, everything is fine in the ordered set, which is not general state space, but at least everything is fine on the ordered set. Sorry, and the random has this expression. If you use this gamma, and H star is density for Q star, but has this form, a mixture of H. So what is going on from here is to replicate the construction on the general space, not ordered space. This is just the ordered space. So we have to extend this for the general space. So now we consider reversible kernel and the non-reversible kernel later on the general space E. So E is bigger than G. So we aim to replicate the construction of Q star that is defined on G, but this time on E. So how to do that? So suppose that there's a sigma-find measure mu, and we have this symmetric function, so reversible function. And how to obtain this? Actually, this is easy because this kind of reversible function is related to reversible kernel. So if H has reversible property and kernel Q has this density, then Q has automatically reversible property. And we want to imitate this construction. So we want to consider a mixture of H and some measures. So let's move on. So we have H. So next is how to consider mixture. So we introduce locally compact topological group. Later, we will introduce order structure in G. And we introduce some scale structure into the space. So this is actually in a kind of assumption. So we consider general state space can be ordered in some sense by using small state G. But there's another assumption. Actually, ordered statistics, it actually works on the scale of the space. So this is a kind of assumption. But under this structure, we can define nice kernels. So anyway, G works like this one. So it's actually a scale of the general state space. So G is from ordered space, and X is from a general space. And we assume that this operation does not break group operation. This is the example. The big space is d-dimensional Euclidean space, and the small order space is positive real line. In this case, this is simple operation, like this one. So now we introduce scale and consider mixture. So first we introduce scale like this to the measure, and this to the kernel. And we want to consider mixture. What kind of mixture we need to consider? But we simply replicate the original construction. So we assume that G has locally ordered topological space. So there's a Haar measure, and we assume that it is also unimodular. So we consider a mixture of nu, like this one for the measure. And we will also consider a mixture of Q, like this one. But mixture of kernel, we need to consider two-step procedure because state itself also has some information on G. So we need to consider two-step procedure. First, we extract the information of G from X, and then consider mixture. The first we extract information of G from X, like this one. So this is a little complicated, but actually conditional measure of this joint distribution. So this is just a conditional distribution of this joint distribution given X. So we extract information G from X like this one. Then we consider mixture like this. Then Q star has this form. So this form of Q star is almost the same as that in the ordered space. So we are almost done. But there are a few things we have to do because at this point, there's no order structure in the general space. So we have order structure in G space, but not general space. We first introduce order structure in X. So to do this, we consider some kind of projection from a general state space to the ordered space. And we consider order by these projected points. So we introduce function delta. So delta is a function from big space, general space into ordered space. And we assume that the function does not break the group action structure. And we say that X to Y is positive direction if we have nice order in the ordered set. So if delta Y is bigger than delta X, we say that X to Y is positive. And we say that delta X is bigger than delta Y, it is negative. So we introduce order in the big general state space. So we are almost done. For example, it's Euclidean, this d-dimensional Euclidean space, and this one-dimensional positive real line. Then, for example, we may consider this as group action. And in this case, square norm will be statistics. So we can compare any state by using this statistics. So if the one is far from the origin, then it is, here we are going to the point which is far from the origin. It is called positive direction. And if we want to go to the point which is close to the origin, it will be negative direction. So we are almost done. And what is the unbiasedness in this space? So it's almost the same. So what does it mean? So in this case, this means all elements, which is it's bigger than x under this scale. This is the same. This is all elements smaller than x under this scale. So we say that if this condition is satisfied, Q is unbiased. So we are almost done. So we define nice unbiased, almost unbiased kernel on the general space, but it's almost done. But the one thing is missing, because in the general space is not ordered space. In ordered space, everything is fine, but the general space is not ordered. So it's almost the same, thanks to the delta function, but actually not the same. Because if you project it into ordered space, everything is fine. So it's nice. But what I want to do is construct nice kernel on the general space. There's a difference. So on the small space, everything is fine. And what we want to do is as follows. We assume the following. The kernel behavior is essentially equivalent of that in the ordered space. Without this, the behavior on the general space and the behavior on the ordered space are different. So we assume sufficiency in a sense. So we assume following as sufficiency. The kernel behavior actually determined by x through delta. So if delta is the same, Q must be the same. Under this condition, the behavior on the general state space is completely controlled by ordered space. And ordered space, everything is fine. So everything should be also fine on the general space. That's the idea. So under this condition, we can show that. And also under some regulatory conditions, we can show that Q star under this construction unbiased. So everything is fine. So you're almost done. So if we have all unbiased kernel, what is going next? So initial plan is completed. We obtain unbiased kernel. So how to construct non-reversible method? This goes as follows. It's almost similar to Metropolis Hastings, but slightly different. If the initial direction is positive, then we use not Q, but Q plus. What is Q plus? Suppose that Q is unbiased. Then we divide Q into Q minus and Q plus. Q plus only jumps into positive direction, and Q minus only jumps into negative direction. The Q is divided into two kernels. And if the initial direction is positive, we will use Q plus. And if the initial direction is negative, we will use Q minus. And if proposal is rejected, we switch the sign from plus to minus. This is the same. If the negative direction is rejected, we switch minus to plus. So this is design. If we have unbiased kernel, we can design non-reversible MCMC like this. And we now have unbiased kernel, so we can design this. So this is pseudocode for MCMC in this way, but we may skip this. It just means as follows. If the direction is positive, we keep the positive direction until rejection and the switch. And if it is negative direction, we keep negative direction until next rejection and so on. So that's almost the same as Metropolis Hastings. but there's direction variable. So this is this is almost the end of the talk. We explain some examples and show some simulations. First, I show first example. So this is sometimes called PCN, pre-condition Crank-Nicholson in MCMC literature. The proposal distribution is AR process. So the next state is proposed by this normal distribution. The center is X. And the next proposal, we consider some effect to the current direction, current point. So this is just an AR process. So in this case, what G looks like, so G is defined by gamma distribution. Why this is important? So I forgot the construction of this. So this is two-step procedure. I forgot this one. Sorry. So if suppose that we are now X, then we simulate G from conditional distribution K, and then simulate Y from this distribution. And we keep going until next rejection. And if there's a rejection, we switch the sign. So K is important. So the step as follows. We initially simulate G from this, and then propose next step by using this. But for the positive direction, if the positive direction is selected, and the negative state, if negative direction is selected. And actually, this is the original PCN kernel has been studied, such as Radford Neal and the Bescos, and also Kotar et al. And the Metropolis version has also been studied, but not non-reversible one. So this is another example. In this case, it's a d-dimensional positive numbers, and J is positive line. Then next state is defined by some sort of gamma distribution with some index. And in this case, K is also gamma distribution. So this is two-step procedure. First, we simulate G from this gamma distribution, and then simulate Y from this gamma distribution. And this is another example. This is also the d-dimensional half-line for the general space, and the d-dimensional half-line for order space. In this case, the next state is determined by beta distribution. And G is determined by product of gamma distribution. And the Metropolis version has been studied by Hosseini, but not the non-reversible ones. And finally, there are some simulation results. So the first example, so first I want to say that the simulation results is not, how to say, it's not super drastical, but because I explained two experiments, but these experiments are not designed for our purpose. It's the general examples. So in this case, we consider stochastic differential equation observed discrete points, and pi here is pi t distribution. So in this case, sorry, next case is logistic regression. So let's check the simulation results. So this is random walk metropolis. This is effective sample size. And this is another PCN kernel. It's not bad. And this is our proposal. And compared to other method, which relates to the derivative operation, these non-derivative methods are better. And non-reversible one is also better. And this is another example. In this case, sometimes derivative-based method works well, but non-reversible one is also nice. So what I want to say is non-reversible methods are robust for many problems. Not just very nice, but very robust. And so this is just an illustration. It's a Poisson hierarchical model illustration. And it's not hard to see, but these two column is reversible method, which do not move so often. And the final column is a non-reversible one. It behaves much better compared to other method, both of which is non-reversible. And these four are reversible. So their final discussions. The Haar mixture method. So in the non-reversible method in this talk is not mathematically studied yet. So we are not so sure about exponential ergodicity or many other convergence properties. So only for air process method, it's very known. But other than that, other methods are not so known. And we can also define multidimensional metric space. And this was studied by Gustafson et al. For reversible method, but we can simply extend it to non-reversible method. And the multimodality, I'm not sure it does work well for multimodality. And there's also, this is non-gradient method, but we may combine with gradient method. But there's difficulty. If we consider gradient method, the order structure will be collapse. So currently, there's no simple way to use gradient method in this framework. There's some work in this, but it's reversible method. And that's it. Thank you for listening.
Thank you very much. Been a very interesting talk. Have plenty of time for questioning. Modulo this microphone. Maybe I can start with some basic ones then. So I should use my own. So can I understand this method and the especially concerning the sufficient statistic as a way to sample? For example, if I think of the circles, so sampling on the circles. First, you sample using Gustafson method on the circles. And then once you pick a circle, you sample along that circle using normal reversible action or normal reversible Markov chain. Can I understand like this way? So you first sample which circle you want, and then you just trace along it, and then you decide, okay, do I now jump to a different circle or not?
So
I'm thinking of it in terms of 2 steps or maybe a transformation. Yeah.
It's not, so the idea is like that. The idea is like that, but it doesn't work so nicely. I'm not sure how to say that, because, so for example, if you consider PCN method, for example, PCN is an air process-based method. So this method, what is the problem for this case? So we can also define like your proposal. We can do non-reversibilization for your method like that. But in that case, we have to change Metropolis method drastically, because usually it's not many method does not satisfy this unbiasedness. So unbiasedness is very important. So if the method you may use is almost works like this, almost like this, but it's not exactly unbiased.
Right.
If you use your proposal. So in that case, we have to change slightly about acceptance rejection procedure.
To account for this.
Some point is nice, but probably some points it behaves poor. So it's a point. So many method works better, but we have to keep in mind that this condition should be satisfied. So it's almost fine, but not always fine.
I mean, that's why you want a sufficient statistic, right? Because
yes.
If the statistic is not sufficient, it means that your space will be too large.
Mm-hmm.
For example, in the circles, that might be a very high dimensional space.
So the idea is almost you're either correct, but slightly different. The idea is almost correct.
Right.
So what I want to do is consider summary statistics, which considered to be how to say from the center to from the origin, and we can go around. It's almost the same, but there's a small gap. But the idea is almost correct.
Any other questions? I can go all day. Is there a connection to the zigzag algorithm, zigzag samplers? Because there also you sample along a direction and then you switch.
That's a good question. So there's some method is related. But most of the case it's different. There's some connection, and the connection we produce very nice method, which is actually under working in progress. But usually it's different structure of non-reversibility. So it's not exactly the same.
Yeah, I mean, zigzag, there's no ordering there, I guess.
But yeah, for one-dimension case, the zigzag sampler is, I think, Gustafson's method.
Yes, it will be in the one-dimension, it will be the same. Yes.
So in one-dimensional case, maybe they're the same. But multi-dimensional case, there's a difference.
Mm-hmm. And one last one from me. So when you had this comparison between the general case and the real case, so there's the order is obviously a factor, but there's also the operation. And this is why I was wondering. So could we then have a Gustafson-like algorithm with a different operation, different inverses? Because as far as I could see, I mean, we didn't have to use addition as an operation.
Yes.
We could have had used a different kernel with our product. And then that could be a different kernel. Then for the same space, we could have two different samplers with different operations. Have you considered like what that how that would affect the sampling?
Other than plus negative, so other than this operation?
Yeah. So there's a group with respect to R plus. You can also have, could you now have a group with respect to our product? And then you would have a different kernel. You would have construction of different Haar kernel, I assume.
Yes, if you, even for the same space, if you consider different operation, they may produce different method.
Yeah,
maybe it's related to the final two examples. So the space is the same actually. So in this almost the same, sorry, not the same, almost the same. So in this case, D plus for general space, and this is also the same. It's the dimension plus for beta gamma counted. What is the difference? This is the difference of the operator. So in this case, summary statistics is just a plus. And in this case, summary statistics is just a product.
Okay.
So it's related to the operation.
Yeah.
So the spaces are the same, but operations are different, and this produces different method.
Right. Perfect. Right, I'm out. Any questions? In that case, we thank the speaker. Thank you. We have 10 more minutes break before the next.